Hello and welcome to Void Electronics. In today's video I want to show you what a multimeter is and how to use it. A multimeter is a piece of electronic test equipment that allows you to measure physical quantities related to electronics. More specifically, it can measure voltage, resistance, capacitance, current, and so on. Let's start with DC voltage. To measure DC voltage, the first step is to configure the meter properly. Now it's on DC volts, and now we have to pay attention to the way we connect the probes. So the negative probe goes to common, and the positive probe goes to the correct input for measuring voltages, which is this one as indicated by the volt symbol right here. And now remember that voltage is the potential difference between two nodes, so that means that whenever we measure voltage, we measure it with respect to something. Here I have a 9-volt battery, which is a good example of a DC voltage source, but don't expect that by simply connecting the positive probe to the positive terminal of the battery, we get a 9-volt reading, because this is not going to happen. That's because the 9 volts that we have on the positive terminal of the battery are with respect to the negative terminal of the battery, so that's how we have to do the measurement as well. So the negative probe goes to the negative terminal, the positive probe goes to the positive terminal, and now we get a proper 9-volt reading. Let's continue with DC current. To measure DC current, first of all we need a circuit, so I'll build a circuit using this 9-volt battery and an incandescent bulb. Now that we have the circuit, we have to configure the meter properly. So to do this, first of all we need to set it to amps. And then we need to disconnect the probe from here, because to measure current you need to connect the positive probe to a different input, which is this one. And now we are ready to measure current. An important aspect of measuring current is that the meter has to be in series, not in parallel. So I will definitely not do something like this, which is connecting the meter in parallel, because by doing this I basically short the battery. And you don't want to do this unless you want to measure the short circuit current of the battery. So the proper way to measure current is to disconnect the light bulb and connect the meter in series with it. So the positive probe goes to the positive terminal of the battery and the negative probe goes to the positive terminal of the light bulb. And now we can actually measure the current through the light bulb, which is about 53 milliamps. And now let's continue with AC voltage. To measure AC voltage, first of all we need to configure the meter properly, so you have to set it on AC volts, and then we need to connect the positive probe back to the voltage input. I will use this signal generator as an AC voltage source, and I will set it to 4 volts peak to peak. And now before starting it, let's make a prediction. What do we expect to see on the meter? Because we could see the peak voltage or the peak to peak voltage, or maybe even something else. So what do you think? Well, we get none of those actually, because here we have a different value of around 1.41 volts. So what does this mean? Well, the clue to this is right here on the meter, because it says true RMS multimeter. So this means that the multimeter actually measures the RMS value and not the peak value or peak to peak value. So the RMS voltage for a sine wave is the peak voltage divided by the square root of 2. So here we have 2 volts divided by the square root of 2, which is the square root of 2, so we get a reading of 1.41. If we actually want to see 2 volts on the meter, then we need to reconfigure the signal generator to 2 volts RMS. And now we get a reading which is much closer to 2 volts. And by the way, the mains voltage, which is 230 volts here in Europe, actually refers to the RMS value and not the peak value of the sine wave. So when measuring AC voltage, you need to be aware of what sort of reading do you want. Do you want the peak voltage, peak to peak voltage, or RMS value? Now let's measure resistance. To do this we have to set the meter on ohms, and then we can simply take a resistor and connect it to the probes to get a reading. As you can see, for this 100K resistor we get a reading close to 100K. However, we have to be aware that resistance is a parameter related to a component, not to a working circuit, which means that whenever we measure a resistor in circuit, there is a risk of getting false readings due to the circuits around that resistor that we are trying to measure. So when measuring components in general, the correct way is to measure them out of circuit. And now let's continue with the most misunderstood mode of the multimeter, which is the continuity check or diode check. In this mode, with no continuity, we get an overload on the screen, and with continuity, we get a beep and a really low reading on the display. For example, this mode is useful when repairing electric guitars because it allows you to check if the strings are grounded or not. If the strings are not grounded, you get really weird sounds in the amplifier, so it's a good idea to check this before anything else. So to do this, you can connect one probe to one of the strings and then connect the other probe to the jack, to the ground actually. And the meter should beep and you should get a really low reading. And now let me show you why I call this the most misunderstood mode of all. Well, that's because not many people know what this voltage on the meter actually means in this mode. The voltage that we see on the screen is the voltage drop across the device under test for a given test current. The test current is specified in the user manual and varies from one meter to another. To show you what this means, I will check a diode because this is what this mode is supposed to check in the first place. So I have here a 1N4007 diode and I will connect it to the meter like this. The positive probe goes to the anode and the negative probe goes to the cathode, which is marked on the diode with a line. And now we get a reading of about 600 millivolts, which is the typical value for a silicon diode at room temperature. To make sure that this is a diode and not something else, we have to check it in reverse as well, and we expect it to be non-conductive. So let's flip it like this, measure again, and we get an overload, which means that the diode doesn't conduct in reverse. And now let's test the resistor as well to see what it reads. So I have here a 6.81K resistor and I will connect it to the multimeter in the same mode. And now I get a reading of about 3 volts. An important aspect here is that if I flip the resistor, we obviously get the same value. So if you want to check a diode, you have to check it in reverse as well to make sure that you're actually testing a diode and not something else. Some multimeters can also measure capacitance. To do this, you just set the meter to capacitance, take a capacitor, make sure to discharge it first because otherwise there is a risk of damaging the meter if the capacitor is charged with a high voltage, and then you can simply connect the capacitor to the probes and measure its value. This is an 820 nanofarad capacitor, but the meter reads about 860. I guess this is within the tolerances of this capacitor. And now let's continue with some simple rules for safely using the multimeter. You have to be aware of the fact that whenever you use a multimeter, the multimeter can measure parameters within certain limits. And in some cases, exceeding those limits can actually damage the meter. And some of these limits are already on the meter's case, we just have to read them. For example, when measuring voltage, the maximum voltage that this meter can measure is 1000 volts. And we also have some limits when measuring current as well. For example, for the lower range, we have a limit of 440 milliamps protected by a fuse. So this input says fused here. And for the higher range, we have a limit of 10 amps. This input is also fused. So exceeding these values will actually blow a fuse inside the meter. And also keep in mind that there is a difference between circuit parameters and component parameters. For example, voltage, current, frequency and so on are related to circuits, so the circuit must be on during the measurements. Whereas resistance, capacitance, inductance and so on are related to components, so the circuit must be off during the measurement, or preferably the component should be out of circuit during the measurement. And now let's look at a practical example. Here we have a Nixie clock that I designed some time ago, and let's assume you want to measure the anode voltage for this clock. As you can see, even though the meter is connected properly, we get a reading of around 0 volts, and that's for obvious reasons. The circuit is off. Let's turn it on and see what happens. So now we get a proper reading for the anode voltage, which is around 230 volts for this clock. Another example would be measuring the current consumption of this clock. So as you can see, we have 0 amps right now, and that's because the clock is off, obviously. And now we have a current consumption of around 470 milliamps with all the digits active. Another important rule is that we have to discharge the capacitors before checking any component on a PCB. And you can easily see with this clock why this is important. So let's turn it off. And notice how long it takes for the capacitors to discharge. At this point the capacitors still hold a relatively dangerous voltage, which could damage the meter if you set it to resistance, continuity and so on. And now let's continue with some details about how the meter works. That's because in my opinion you really need to know how the meter works up to some extent if you want to use it correctly. And that's because multimeters are not ideal. What I mean by that is that multimeters can actually change the circuits that they are measuring, so you have to understand their limitations in order to use them properly. The only thing about this is that I need 2 multimeters to demonstrate this. Let me see what I can do about this. Okay, with this issue sorted, we can continue with our topic. Let's start once again with DC voltage. When measuring DC voltage, we have to keep in mind that the ideal voltmeter has infinite input impedance. The only thing is that there is no such thing as an ideal voltmeter. So any voltmeter has some sort of finite input impedance, and this input impedance can actually drag down the voltage that we're trying to measure. So we can find the input impedance of any voltmeter in its manual, and if you're not sure about it, we can always check it using another multimeter. So in this case, the left multimeter measures voltage, and we can use the right multimeter to study the left one. So let's set it to resistance, and as you can see, we get a reading of about 11 megaohms. This reading is close enough to what the manual says, which is about 10 megaohms of input impedance. If you're like me, then you don't simply believe whatever random guys on the internet say. So here's a proof for the fact that the input impedance of voltmeters actually matters. So here we have a simple voltage divider made out of 1 megohm resistors. The ends of the divider is powered by this power supply, which provides 10 volts. So by doing the math, the middle node should be at around 5 volts, right? Well, let's check the middle node with this meter first. So here we read about 850 millivolts. So we are far from what the theory says about the middle value. Now let's repeat the measurement with the meter on the left. And now we have 4.7 volts, which is not 5 volts, but let's say it's close enough. So now you may be thinking that one of the meters is faulty, right? Well, there is only one way to find out, and that is to connect both of them at the same time. Please notice what happens on the left multimeter when I do this. So now both meters read about 850 millivolts. And that's because the input impedance of this voltmeter is so low that it drags down the voltage divider. As I said, when measuring voltage, any voltmeter has an input impedance. And in the case of the digital one, the input impedance is 10 megohms. For old multimeters, the input impedance was specified in ohms per volt. So in our case, for DC voltage, the input impedance is 20 kilo ohms per volt, and we are on the 5 volt range, so the input impedance is 100k. And once again, if you're in doubt, you can simply measure the input impedance of your meter. So in this case, we have the meters connected together once again, and you can see the input impedance of the right meter on the left one, which is about 100k as I said, and this impedance changes by changing the voltage range. So this is for 5 volts, for 25 volts it's higher, for 50 volts it's even higher, and so on. Of course, we have a similar situation when measuring current. That's because an ideal ammeter looks like a dead short. But there is no such thing as an ideal ammeter in real life. So any ammeter has some sort of internal resistance that can actually change the circuit we are trying to measure. This internal resistance causes a voltage drop across the ammeter, which is called the burden voltage. To demonstrate this, we can use another multimeter set to ohms, and we can get an ohms reading of this ammeter, which is about 2.14 ohms. And using the continuity mode, we can also measure the burden voltage in these conditions, which is about 2.1 millivolts for a test current of around 1 milliamp. And now let's see how the meter works when measuring resistance. To measure resistance, any multimeter applies a test current and it measures the voltage drop across the device under test. So if you paid attention, you notice that we have the same experiment as before, but the meters are now switched. So this one measures resistance and the other one measures current. So when measuring resistance, as you can see, this meter applies a test current of around 1 milliamp and measures the voltage drop across this meter, and then using Ohm's law it can calculate the resistance, which is about 2.2 ohms. For continuity or diode mode we have pretty much the same thing. So the meter applies the same test current, but now it displays the voltage drop instead of the resistance. And now let's see how the meter works when measuring capacitors. If we think about it, measuring a capacitor is a pretty difficult thing to do. So let's see how the meter does that. To do that, the test setup is pretty simple here. We have the multimeter connected to a capacitor, and the capacitor is also connected to the oscilloscope that we have here. So we can set the meter to capacitance, and now I get a really interesting waveform on the oscilloscope. And this waveform is a clue to how the meter works when measuring capacitance. The meter takes advantage of one of the fundamental equations of the capacitor, which is I equals C times dV over dt. Basically, by charging the capacitor with constant current between two voltage thresholds and measuring the charge time, we can find the capacitance value. So the duration of the ramp that we see on the oscilloscope is directly proportional to the capacitance. Another reason for calling this a really clever solution is that the meter can already measure time intervals. That's because it can measure frequency. So with some extra circuitry, the frequency measurement circuitry can measure capacitors too, which I think is brilliant. So if you like this video, please give it a thumbs up, and if you're interested in more content related to electronics and programming, please subscribe to this channel because there is more content like this on the way. That's it for today. Bye.